All right, everybody, let's get started. I did speak to my TA over the weekend. I know he said he knows he's a little behind on the homeworks. I checked it yesterday. He still has the welding assignments to do, but he said he's going to try and catch up on that this week. But we are going to keep on pressing with the homework schedule where we have a homework each day, do the following lecture, and then the lecture after that, the solution will be made available. So for instance, if you look right now, you'll see the solution to homework 5.2 is posted, right? So 5.3 is due today. On Wednesday, the solution to 5.3 will be posted, and it'll keep going like that to the end. Today is our last lecture on columns, okay? And for the rest of the semester, we are going to focus on beams, okay? So the first lecture will sort of be to get a handle on some of the basic concepts from Engineering 216 that I know that will be just a formal review, right? Because y'all are good with that stuff, right?
Oh, yeah. Was that the class at 8 a.m.?
That's the class I'm teaching at 8 a.m. this semester, I can tell you that, over in Corbly. So
You got that many people?
I got 52 people in there, so yeah, in the wonderful world of Engineering 216. Okay, so what we're going to do today is we're going to do another column design problem, but this one's going to be more involved, okay? The one that we did last time, the column design problem that we did, it really sort of ended once we picked our shape. We computed the capacity, but we did that more as a means of a formality. We knew it was going to work because we didn't have to do any linear interpolation, whereas with this, we are going to have to do linear interpolation, and the process is the same, but actually checking it out is going to be a little bit more involved. Okay, so let's recap. Let's make sure we all know the basics. So first off, your K values for analysis and design. The problem that we're going to do today, I went ahead and just gave you the K values because I want to get the problem going. But keep in mind that you can always find these on 16.1-570. That is a tab-worthy page in the manual. Remember, we're always using the recommended values, not the theoretical values. In most cases, bumped up just a little bit to account for variances in theoretical versus real-world conditions. Not all of them, like the pen boundary condition still won, but most of them are bumped up a little bit. All right, the analysis method, method number 1, which is just chugging out the expression. I'm hoping by now that you're comfortable with that if I give you a column, you could just compute the capacity. Is that a fair assessment? Does anybody have any questions about that? I'm hoping that's pretty simple. Okay. Just to make sure that we're clear, we determine the largest KL over R, and then from KL over R, we determine FE. FE we use in our expression for F critical, and then phi F critical AG for the capacity. Okay, now here's analysis method 2. What we do is we determine the largest KLX and the largest KLY, and we consult table 4.1a for the capacity. And 4.1a is used if we have 50 KSI steel. If we have 65 KSI steel, we use 4.1b. 70 KSI steel, we use 4.1c. We will not be using those, even though the process is pretty much the same. But the idea is that if your KLY is bigger, then you know that weak axis buckling is going to govern, so just look up the capacity. But if KLX is bigger than KLY, then it might govern, it might not, you don't know. So you look up the capacity based on the larger of KLY or KL effective. And KL effective is just KLX divided by your ratio, your RX over RY ratio. More often than not, you will need to linearly interpolate in table 4.1a or in just table 4.1 in general, so make sure you have that equation handy. We're going to do a fair amount of interpolation today, so make sure that you're comfortable with that. Now, in terms of design, what we're going to do is we're going to determine the factored load on the column, and then we're going to determine the largest KLX and the largest KLY. And here's how it's going to work. So we've got a load, we've got the largest KLY, we're going to select a family of trial sections. So at least one W14, W12, W10, W8. Now, maybe not all of these are possible. Maybe only some of them are possible. Maybe only some of them are available. It's very possible that under given loads that a W8 may not work. Like that, there's not very many of them and they're pretty small. But you'll probably have at least one W14 and one W12, and in most cases you'll have a W10. So you have a family of these shapes. Now you have to check them. Now you don't have to check them if weak axis buckling governs, and you know that's the case if KLY is bigger than KLX. Like that's fine. From the group of trial sections, just select the lightest one. But if KLX is bigger, for each trial section, you have to verify the capacity. So from a group of 3 or 4 trial sections, maybe only 2 or 3 of them work. Maybe only one of them works. And from the ones that work, select the one that's the lightest. And then make sure, once you've done this, that you analyze the chosen column using method 1 to verify its capacity. Any questions? All right.
The one we have to test each of them?
Yes.
Want us to compute the efficiency for each of them?
That's a great question. So the question was, if the ones where you have to test each one, do I want you to compute the efficiency? The answer is no, okay? The reason why is because in inelastic buckling land, the efficiency doesn't matter all that much. Let me give you an example, okay? The homework that you just did, you selected a family of shapes for problem 2, and 2 of them had the same capacity, right? Like they had the exact same capacity. Both had, what was it, 631 kips? 633. Okay, all right. But that didn't matter, right? One of them was lighter than the other. It doesn't matter what the efficiency is. You're still going to go with the lighter one, right? Even if they had the same efficiency, right? It just doesn't matter. So that's going to happen. And there's going to be some. So when we get into continuously braced beam land, like we're not going to find this just in columns. We'll find it in beams too. When we get into continuously braced beam land, what we'll find is that the manual, the design aids that we use for beams, the manual groups them according to their economic efficiency. And they'll be, like, you'll go into the manual and you'll find the most optimum shape from an efficiency standpoint. And that'll be within a group of like 12 shapes. But the shape on the very top is the lightest in that group. So you just go with the lightest one. Even if it's not as efficient, it doesn't matter. You're not going to spend more money just so that your efficiency ratio is 90% or more. We don't care if it's cheaper, right? Does that make sense? That will make sense a little bit more when we get into column and beam land. Any other questions? This is really good stuff. I like this. Okay, so column design example 2. So one of the things with this column, I went ahead and gave you the load. Let me go to the notebook because I already have it right here. Let me make this a little bigger. Oh, that's not what I want to do. I want to do that. There we go. All right, so we're going to determine the lightest W shape for this bracing configuration and this load. So I have a 32-foot long column that along the x-axis is pin-pinned, but along the y-axis is it's pin-pinned as well, but it's braced in the middle. So K is 1 for all segments, but for the y-axis, we have a KLY of 16 feet, and for the x-axis, we have a KLX of 32 feet. So it is definitely longer along the x-axis than it is the y. So that's going to change things in terms of how we compute the capacity. Before, we looked up a section, we knew it worked. Now, we may not, maybe not. We don't know. So we'll have to check that and see. So. And that will be that'll be clear as we start doing some page flipping and whatnot. So I'm going to give you a sec to write this down because we're going to be doing some interpolation, going to be doing some page flipping. So let me get my notebook here. All right, everybody good? Okay, so let's get to it. So one of the things that I did with this problem is I wanted to make it a little easier as we start getting into column land, because if we go off of our procedure, right, step 1 says compute the factored load. but I gave that to you. I just said PU is 650 kips. Okay? I gave that to you because I was like, let's just move on. I think you all know how to do 1.2 dead and 1.6 live at this point. 2, compute the largest KLX and KLY. So KLX is just going to be 32 feet. KLX is going to be 32 feet, and KLY is going to be 1 times 16 feet. If I went too fast on that, stop me. But I think that's simple, right? That should be straightforward. Okay. All right. So now let's get into it. Okay, so we need to select some trial shapes. All right, and so we're going to select that based off of PU is 650 kips and KLY is 16 feet. So maybe I'll use brackets there. Okay. So, same process as we did in our last example. So we're going to open up our AISE 15th edition steel construction manuals. We're going to open them up to table 4.1. And we're going to ask ourselves, okay, let's look at our trial shapes. So a W14 by something. B, a W12 by something. C, W10 by something. And by something. Okay? Yes?
Why did we pick 16 and not 32?
That's a great question. Okay, that's a great question. So the question was, why did we pick 16 and not 32? Okay, I want to make sure that we're clear on this. Okay, the reason why we're picking 16 is because right now what we're doing is selecting trial shapes. Okay, and if you look on the very left of table 4-1, what does it say? It says that the capacity is reported with respect to the least radius of gyration Ry. So we have to go into table 4.1 with the data from the y-axis in order to select a trial shape. But we're not going to end this problem right after we just pick these shapes. For each one of these shapes, we're going to have to verify their capacity using the x-axis. So we're not ignoring it. We're just going to deal with it here in a little bit. All right? All right. So let's start off with the W14s. Does anybody have for me a W14 shape that will withstand a load of 650 kips, given that the column has an effective length of 16 feet? Everybody had a shape for that? The 82, okay? Now I'm going to ask for a little bit more data. Okay, I want to know what the phi-pn is under that, under those conditions. What is the phi-pn? 697, and this is what I asked for last time, but what I didn't ask for last time was the Rx over Ry ratio. What is that? Remember, you get that from the bottom. 2.44. Okay. All right, good. Now, the 12. 72. Now you chose that because it has a phi-pn of what?
709.
And what is its Rx over Ry ratio?
1.75.
Okay, good deal. Now, what about the W10? 77. Okay. You chose that because its VPN is what?
686.
And its Rx over Ry is what? All right. What about the W8s? None. The heaviest W8 just doesn't cut it. So we'll say W8, none applicable. Okay. All right, I'm going to stop for a sec. I want to make sure everybody's caught up with me because I want your attention on what we're about to do next. Now, there is a number I want burned into your head for this problem. And for those of you wondering what I'm writing on the board, it's that PU is 650 kips. I want that number burned into your head as we do this example. What is this number? This is how much this column has to hold up. Okay? Think about that. All right? With me so far? Now, before the example that we did on Friday, what we would have done is we would just, which one would we have picked? We would have just went with the W12 by 72, right? Now, the reason that we were able to do that in the last example is that we had the same KLX and KLY. So we knew that the weak axis was going to govern, so we didn't have to check the strong axis. We just looked, that's the lightest one, boom. We don't know that's the case with these columns because we have a KLX of 32 feet and a KLY of 16 feet, okay? So now we have to check each one of these to see whether or not they're going to work. And from the ones that work, select the lightest. Now, before we start doing math, some of the efficiency-driven engineers out here, and I don't mean efficiency in terms of PU over VPN, I'm talking about efficiency in trying to make your homeworks as short as possible. Some of you are going to look at the order in which we do this problem and go, isn't there a better way of doing this? Yeah, there probably is, and I will talk about that near the end. But I kind of want to go through these in order because there are some patterns I want you to see with each of these shapes. There's a specific, I chose this problem for a very specific reason, to teach you all about some patterns that you might see when you do homeworks and exam problems, okay? So just bear with me, all right? So we're going to check each one, all right? So I'll call this, verify capacity. Verify capacity based on the strong axis. Okay, and so we're going to take each shape one at a time. All right, so let's start off with shape A, which is the W14 by 82. So what is KLY? It's 16 feet. What is KL effective? It's KLX over RX over RY, which is, here I can make that a little better. So 32 feet over, now what is RX over RY for the shape? What is it, 2.44? And just so you're aware, I am going to be doing this problem a little bit inefficiently for the start because I want to make some points, okay? I think it's easier to make those points when you go through it and you go, I didn't need to do that. Then you'll see it. So what do I get for this? We'll say the 2 decimal places. 13.11 feet. Okay? So let's look at a couple things. So let's say I wanted to determine the capacity based on an effective KL of 13.11 feet. Sounds to me like what I would need to do is look up PN at KL is 13 feet and PN at KL is 14 feet. Let's go ahead and look those up. All right, what is it for 13 feet? What is my capacity for 13 feet? 772? Is that right? Wait. Hold on. So this is 772. This is 809. All right? So would you agree that the capacity according to this value is going to be somewhere in between? Would you agree with that? How would I determine that capacity?
Interpolation.
Now, before you all start chugging ahead with your Casio FX115 ES pluses or similar scientific calculators, I ask you, is it necessary? You're shaking your head no. Why? Because what did I tell you I wanted you to have fixed in your head? This number right here. This is how much our column has to support, right? And I don't care what your magical linear interpolation yields. It will be somewhere between these two values, right? And if it's somewhere between these two values, I don't care what it is, it's bigger than that, right? So is the W14 by 82 a viable section? Yes. Okay. Now we're going to go one step further here. So first off, I'll say by observation, W14 by 82 is okay. But I'll go one step further. Here's KLY, which is 16 feet. Here's KL effective. KL effective is 13.11. I would argue that because KL effective is smaller than KLY, what does that mean? If KLY is bigger than this, what does that mean? Exactly. It means the weak axis buckling governs. What is the axial capacity of the W14 by 82 under these bracing conditions? It's that. It's 697, right? That's the capacity, right? It's not these, right? Because let's just make up the number. Let's say that I interpolate this and I get, I don't know, 801. I'm just making that up, right? 801 kips would be the axial capacity for the strong axis. But for the weak axis, it's 697. Does that make sense? So I would argue that just by looking here and here, I didn't even need to write this stuff down. It was like, I know what the capacity is. PPN is 697. Does that make sense? Is everybody okay with that? So again, like I said, I admit I'm doing this a little inefficiently, right? But I want you, it's almost like I kind of want you to go through and go, oh, I didn't need to do that. And once you recognize you don't need to do that, it makes it a little easier as you start doing homeworks and exam problems. With me so far? Okay, now, let's see if you're paying attention. So the W14 by 82 is okay. Let me ask you a question. If the W14 by 82 is okay, is there value in even assessing this section? It's lighter, right? So exactly, right? If it was heavier, I probably wouldn't bother with it, right? Does that make sense? There's no point, right? Who cares if it works? I'll say if this was a W14 by 90 something, I don't care if it works. That's less money, right?
Does that mean you could just go ahead and do the lightest member first?
See, all right, now that's the question I was waiting for. Is like, couldn't you just start with the lightest section as soon as you get one works, just stop the problem? You are 100% right, right? 100% right. However, in this class, we're going to do all of them because I want you to see the patterns associated with all of them. With me so far? That's why we're doing it. It's more from an educational perspective. But your statement that I'll just start with the lightest one and work my way down until I get one that works, totally fine. Totally fine. All right. So for the 12 by 72, we have KLY again, 16 feet, but the KL effective is KLX over RX RY. So 32 feet, but now we have a different RX RY. We have 1.75. Sorry, 1.75. That's a unitless value. So what's this? 18.29. Do I have a second? Okay. Now, so help me out with this column. Which axis governs for this column? The weak axis or the strong axis? Strong. The strong axis governs, right? Do I need to look at the values in the manual? Yeah, I do, right? So what I need to do is I need to say, okay, VPN at KL is 18 feet, and VPN at KL is 19 feet. So what do we got for these? Let's do the 18 feet and the 19 feet. 656 and what? 656. $656 and $629. So our capacity is going to be between these two, right? Is there a chance this column is going to work? Yeah, you're right, right? He's like very small, but there's something to that, right? Because this value is in between these, right? Just depends on what works, right? So let's see. Let's follow our linear interpolation. So let's look at this. All right. So what do we got? We got x1 is 18. Y1 is 656. X2 is 19. Y2 is 629. X is 18.29. Y is, I don't know, right? So Y equals Y1 plus So what do we get for this? It's like I said, we need to interpolate. It might work, might not. I mean, if you can eyeball it, hey, eyeball it. I'm not that good. I kind of need to do the math. Say it again.
I think you did it wrong.
I did it wrong?
Yeah, 656 and 629, they both got to be the same Y1.
Oh, yeah. Whoops, yeah. This needs to be 656. Yep.
And you get 648.17.
640, so like 648.2?
Yeah.
All right, did I second on that? Okay, all right. So therefore, what we're finding is that a VPN at KL is 18.29 feet is 648.2 kips. Now remember, our PU was 650 kips. What does that mean? It doesn't work, right? It's no good, right? So therefore, the W14 by 82, or sorry, the W12 by 72 is no good. Was it still worth checking? Yeah, it was worth checking, right? It was definitely worth checking because if it did work, it'd save us some cash, right? With me so far? So I want to stop for a second, see if this made sense. Does everybody, I want to make sure that everybody understands the observation why the strong axis governed, because KL effective is bigger than KLY, how we looked up these values, how looking at these values we saw that linear interpolation was necessary, and how when we do the linear interpolation, we see that the column just doesn't quite have enough capacity. Everybody good? Okay, so now let's check the W12 by 77. Or sorry, not the W12, W10 by 77. Let me start off by asking a question. Is it worth it to even check this section?
Yes.
You say no. Why? What's the only section that we have that works right now? The W14 by 82. If this section works, that'll save us some cash, right? Because it's lighter, right? So it's at least worth checking, right? But if it doesn't work, we still have a shape that's valid, right? Okay. All right. So it's worth at least checking, okay? So again, we go right up here. So KL, hold on. KL Y is 16 feet, and KL effective is KLX over RX over RY. And what was that? It was, and what do we get? 18.5. Well, that's nice, right? From a linear, why do I say that's nice? It's so from a linear interpolation standpoint, I could just average the two, right? Like whatever my value is here, whatever my value is here, just average them and boom. But for the sake of discussion, I want to live in a world where it's not nice. First off, what does this tell me looking at these two? Strong axis governs, okay? So it also tells me I need to pull the capacities for KL is 18 feet and KL is 19 feet. So let's do that. VPN at KL is 18 feet. VPN at KL is 19 feet. Now I already hear some whispers because I think you all are probably getting my point here with this one, but let's just be formal with it. Let's just write it out. So what are we getting for 18 feet? 617. And what about for 19? So why am I hearing these whispers? Why? I know why, but I want somebody to say it. It doesn't work, right? It really doesn't work. Because, well, here's the thing. So PU is 650 kips, right? This is the number I want burned into your head for this problem, right? This is how much force the column needs to withstand. I don't care what linear interpolation yields. It doesn't matter if this is a nice, pretty number or not. It's somewhere between here. What's it going to be, like low 600s, like 590, something like that? It's not enough, right? Was it worth doing the math to check the section? You bet, because if it had worked, it would have been lighter than the 14 by 82. But does it work? No, right? So what I would say here is, by observation, is no good. So before, what we did is we looked at shape 1 and we said, well, by observation, we know that the W14 by 82 is okay. Whereas with this last shape, we're looking at it and we go, I'm not going to waste my time doing the linear interpolation. It's not going to work, right? It's not going to. So what's the answer to this problem? I needed to select the column to resist these loads. What column am I going to pick? The W14 by 82. Now, with all this linear interpolation and all this checking, what do you think I ought to do? Just check this column using method 1, right? Just calculate the capacity and make sure it works. Treat it like a regular old problem. So And this is a simple part. So step 5. Analyze the W14 by 82 using method 1, just to make sure it works, okay? Just to make sure. Again, we're talking about a column that needs to hold up 650,000 pounds. I think it can take another 5 minutes of calcs just to make sure that it's good. So, okay. So we have AG, RX, and RY. Now we know that this is 24, 6.05, and 2.48. First off, you should at least be able to see the gross area and the RY from the bottom of the page, but RX isn't reported. I kind of wish it was, but yeah, we can at least get those. We know that FY is 50 KSI steel, or sorry, FY is 50 KSI because it's A992 steel. And we know that E is 29,000 KSI. Now we know that KLX is 32 feet and KLY is 16 feet. So what do, right? So we'll call this, sort of step 1, 5.1, compute largest KL over R. So KL over R in the X direction is 32 feet over 6.05 inches. Anybody have a problem with that? Hopefully you do. Units. We do the same thing for the y-axis. So what do we get for KLX, or KL over R in the X direction? $63.471, something like that. How about for the y-axis? Hold on. You might want to check that. You probably use 32 feet? Yeah. Okay. What does this tell me? Which axis governs? The weak axis or the strong axis? The weak axis. Now, here's something. Let me ask you this. So, weak axis governs. Did we get that before when we looked at the W14 by 82? Is that what we found before? I think so, right? Because when we looked at the W14 by 82 up here, right, here's step 4, we got that KLY was 16 feet and we got that KL effective was 13 feet, so that told us that the weak axis governed. Same thing, same story down here, right? So 5.2, compute FE. So all right, so what do we got for FE? Yeah, that I was gonna say that. Yeah, say it again. All right. So 5.3 compute FCR. So we have, so for FCR, we've got KL over R, which is 77.419, and we compare that against 4.71 square root of E over Fy, and the 4.71 times the square root of E over Fy. My E's don't quite look like E's sometimes. Yeah, it's like 113.4. You know, the more you do this, the more some of those values kind of just, pop up out of your head. I usually try and just make sure that I'm being formal with it, but yeah, as you start doing this, it kind of, you're like, oh yeah, I remember that. So therefore, FCR, which one do we use? Do we use the 0.658 with the exponent, or do we use 0.877 FE? With the exponent, yeah. So, bless you.
Where's that factor at again?
What factor?
Where it has that, which one you pick in the manual.
Oh, so let me pull that up here in a second. I'll show you. But let me finish this calc and I'll show you. So
I tried to look for it in the book and then I just had to go to the lecture notes.
no, I'll show you. It's a fair question. And so when we chug this out, what do we get? Remember, that fraction is an exponent. It's not multiplied. $32.26 KSI. Do I have a second on that? All right. So and then that was 24.0 inches squared. And so what do we get for that? 696.8. Do I have a second? So a couple points. So to be clear, so what's the answer? Use a W14 by 82. Okay? And don't worry, I haven't forgot your question. I'm going to get to it. Now, what did we get? 696.8 round up to 697. Remember, when we selected the W14 by 82, what did we select it based off of? A capacity of 697, right? And we ended up finding that the weak axis buckling governed for that shape, and so the capacity that we looked up, that was the capacity. So this is just us checking it. Now, I'm going to say one other thing about efficiency, and hopefully this problem really drove it home. Does efficiency really matter? I mean, think about it. This was the lightest W14 that worked. This was the lightest W12 that worked. The next one was the lightest W10 that worked. Hey, think about it, right? Does the efficiency really matter? Okay, let's say it did matter. What are you going to do? Pick the next lightest shape? We just did. It didn't work, right? It doesn't matter, right? So that's sort of the point that I'm trying to make when it comes to sort of breaking you on this whole like efficiency things. When it comes to columns and beams, tension members, that's another story, but columns and beams, not It's not that it's not important. It's just that our procedure has been defined to pick the lightest shape available. Like, you know, it's like that's it, you know. So, okay. Any questions about this? Now I want to answer your question. I want to make sure that you're clear on this because this is important. I want everybody to turn to page 16.1-35. Just to make sure that everybody sees this. So we're in the manual now, and we're in the specification. We're in chapter E. So it's right near the shear lag factors. Okay? So if you go to 16.1-35, right, and look at the bottom, you should be in section E3. You see that? So section E3 shows the flexural buckling of members without slender elements, and it tells you how to compute FCR right here. Now, one thing that's new about the notation is it says, instead of KL over R, it says LC. Does everybody see that? Turn the page, and what is LC? Wait, hold on, or is it? No, sorry, it's on the previous page. Sorry. If you go up to section E2, what is LC defined as? KL, you know what I mean? So the reason why the manual uses the term LC is because it is analogous to a term utilized for beams, which is LB. So they're trying to use common notation so that when you see this stuff, you're like, oh, I kind of get what they're talking about. Because LB for beams, conceptually, pretty much means the same thing as LB or LC for columns. It's just how far apart your braces are.
What about the FY, where it says or FY over FE is less than or equal to 2.25?
That's a great question. So So let me explain that. So there's a question about if you go to 16.1-35 and it says when KL over R is less than or equal to this, or when FY over FE is less than or equal to 2.25. Those mathematically pretty much mean the same thing. So if you wanted to compare FY over FE, or if you wanted to compare KL over R versus that limit, you could do either one. There is a reason that I like to do the first one. Well, there's two reasons. One, the first one tethers more to the FCR plot in general, which was the original model that was developed. But two, and I'd have to check the bridge spec. I don't think the bridge spec uses that. They might, but I think when, at least under, maybe it was either ASTRO 5th or ASTRO 7th, they didn't use that. So one of the things that the spec bodies do a pretty good job on is they try and write different specs so they use common terminology and common phraseology. But usually what happens is like this is first, and then like other specs get adopted later. I haven't checked this section of the spec to see, in the bridge spec to see if it refers to FY over FE, but numerically it's the same thing. It doesn't matter. It's like, for example, what is FY over FE? What is 50 divided by that? Well, it's less than 2.25, so you're using this equation. So it means the same thing. So, yes, sir.
So the W12 by 72, the next size up is a W12 by 79, which is still wider.
That's a good question. That's a great question. Man, you stole my final point. That you could maybe check the W12 by 79. You could maybe go back into the manual and see maybe there's one that's a little heavier. To be honest, I'm not going to make you do that. I'm not going to make you do that. That rarely happens, but it does every now and then. It did in this case. So I'm not going to make you do that, though. I'm not sure if it worked or not for this problem. I'm going to go out on a limb and say I don't think it did. So there was a homework assignment, though, which I gave last year. I didn't do it this year, but there was a homework assignment last year where what happens is you check all of them. Like you check the W14, the W12, the W10, W8. None of them work. Then you have to go to the next heaviest W14, W12, W10, W8, and then like one of them works. So you had to go through like 6 or 7 of them before you found one that worked. Well, let me say this. It's not really so much me being mean. It can actually happen in real life. It will happen. The bigger chance of that happening is when your KLX and your KLY are really far apart. Like when you have a KLY of 10 feet and a KLY of 40 feet, get ready to do some page turning because you're going to have to go through a lot of sections to find one that works. So,
It's
yeah.
a safe assumption. So like how when we done the W12, it's for the weak axis on 16 feet. It had a lower KLR or KLX or RX over RY, and it also had a lower theta PM 16 foot. So like if that was lower than like how that's.
I know what you're saying. I do. And because the curve is so nonlinear, I wouldn't. I know what you're trying to, I would kind of just do it because again, you're dealing with a really nonlinear curve and it's really sensitive. Like the stuff that you're talking about can get kind of sensitive depending on what your RX and RY is. And yeah, I would just do it. Now, it can help your gut feeling, but I would go through it. So, because stuff like that, when you get into stability design, it's good to have a gut feeling, but you should just go through it. So, like when we start using the beam charts, don't even try to be prophetic about it. Don't even. So, we're actually running out of time. Any questions? Yeah. Yes. Real quick.
How would we do it, like, if our beginning, like, KL values were not full numbers? Like, how would we, like...
Oh, that's a great question. How would you... That's a great question. That would make it harder because what you would have to do is you'd almost have to, like, interpolate for the design, right? I can tell you what I would probably do is I would probably round up to the next nearest whole number, pick shapes, right? But then do what Mr. Trogdon said, which is like there might be one next lightest one that might work as well. So I would go through this process to select a family of trial shapes rounding up. But then when I got my shape, I might just check the next lightest one just to make sure. So I'm not going to do that to you. Don't worry. I'm not that much of a jerk. I'm a little bit, but not that much. All right. Any questions? All right. I left the QR code on this screen if you need to get it. I will see you all on Wednesday. We're going to talk about beams. Fun, fun.
If K times L is the effective length, and we compute KL effective, does that mean we're computing the